The physics system in Unity doesn't just allow us to model forces such as gravity and drag. It also provides a mechanism by which we can influence the collision system so that we can make it appear to the player of our game that certain surfaces have different surface properties. To use an example, let's imagine that we have a hill that is covered in grass. And halfway up that steep hill we have a brick wall. And imagine we have a brick in our hand and we throw it at the wall. What would happen in reality is that brick would hit the wall, most of its speed would be stopped dead, and it would fall to the base of the wall onto the grassy slope. And providing that the slope wasn't wet, the brick would probably come to rest very, very quickly, because the grassy hill provides a lot of friction, and the brick itself is also a pretty high friction object. Then imagine the same scenario where that wall is halfway up a hill that is made of just pure ice. In that case, the brick would hit the wall, drop to the base of the wall, and then would begin to slide all the way down that icy hill. And this is what physics properties allow us to do. And it does this by allowing us to model friction. And it does this by dividing its friction calculations into two groups: dynamic friction and static friction. And the static friction describes the properties of the surface with respect to an object that is currently stationary on that surface. It's like how much force is needed to get it to move once it's kind of at rest on that surface. And then as a different kind of group of calculations, with a different group of settings, it allows us to specify how objects already moving across that surface have their velocity affected. And this is the dynamic friction that I was talking about. And we specify these properties in what is called a physics material. And if we go down to the project view and click on the create button, we can see that one of the assets that we can create is indeed a physics material. But before we do that, it's no point adding a physics material if none of our objects are yet interacting with one another, or we won't actually see the surface dynamics in operation. So the first thing I'm going to do is write a very short one-line script that is going to launch the ball down the bowling lane. Okay, and then we can study and change the way that the ball and the bowling lane surfaces interact with one another. So I'm going to go to my project view. I'm going to click create new folder, and I'm going to call this folder scripts. And then I'm going to right click on the folder and create a new C# script, and I'm going to call this ball. And then I'm going to open up the ball script in MonoDevelop, and as we have seen before, this automatically creates my new ball class derived from MonoBehavior, the class we know that our components must be derived from. And I'm going to remove the empty update method because I don't need that, but I do need the start method. And what I'm going to do in the start method is I am going to tell the rigid body that its velocity is currently 10 meters per second in the direction in which it is facing. Now, because this function only gets called once, all I'm doing is setting the initial velocity, and then from that point on, with every update, I'm letting the physics system itself diminish the ball's velocity as it rolls down the alley. Now, obviously, if I was to set the rigid body's velocity every frame, that would not be good, because in many ways I would be overriding much of the physics system's calculations. After all, part of what it's there to do is to determine the velocity of your object at any given time. But because the start method is only called once, I can set the velocity as a one-shot deal, almost like I'm applying this one-shot instant force to the object to propel it down the alley. So how do I get the rigid body component? Well, as we've discussed before, one way of doing it is like that. But we don't have to do that, because just like we saw earlier with the transform component, which had a shorthand C# property to allow us to access it, so too has the rigid body. So we can access the rigid body of the object just like that. So what I'm going to do is I'm going to say rigid body velocity, And now the important thing is that this isn't a local velocity, this is a world velocity, so a world space velocity. So what I want to do is I want to tell it the actual direction and the magnitude in which to travel in world space. And fortunately the transform of the same game object, because bear in mind this will be attached to our ball, has a property called forward. And this gives us the world space forward vector of our game object. So I know that if I were just to assign this forward vector to our rigid body velocity vector, what I would be specifying is that I want to the initial velocity of the ball to be 1 in the direction of this yellow arrow here, down its local forward vector. But I don't want it to be 1, I want it to be a bit heavier than that, a bit faster than that. So all I have to do is just scale the forward vector by the power that I want, and I'm going to multiply it. I'm going to multiply it by 9. Okay, so we're now saying that we want the velocity to be 9 meters per second initially at the very start of this application, and we want that that velocity in the direction that our game object, or at least the transform connected to our game object, is facing, which of course is exactly the same thing. So I'll save that off. Now this is just a temporary script. We'll get rid of this in a moment because let's be I've actually got a error there, and when you have an error like that, you can look at it in the console view, and if you double click on it, it will bring the line up, and you can see that what I've done is I've spelt forward without an R, and that's not cool. So Unity didn't like that. It didn't want to play with me anymore. So all clear, been recompiled, and now we need to drag the ball script onto our ball game object. I'll call that ball. I thought I'd done that already. And there you go. If I just close up the material a minute, you can see that our ball object now has quite a few components. It has the transform, the mesh filter containing the data, the sphere collider, the mesh renderer containing its material information, rigid body containing all that information, and it also has the ball script that we've just written. And if we go down the other side of the alley when we run this, we'll see how the ball and the alley interact together. So let's press play and see it in action. And there it is rolling down the alley, and look at that. I'm not even sure it's going to make it. Oh, it did, but let's be honest. Boosh, it's a bit lame. And I think one of the reasons for this is the physics material, because what's happening is that ball really did slow down quite a long way when it first hit the alley, and you can look at the speed being killed off there. So now we've got the ball and the lane, or alley as I keep calling it, interacting. Let's now have a look how physics materials can play a part to change the way in which those two surfaces interact. Okay, so we know we want to create some physics materials, but where do we put them once we have them? And the answer is on the colliders of our objects. So each collider has collider component, has one of these material properties which allows us to drag and drop a physics material onto it. So let's go to our project view and do create new folder, and we'll call this folder physics materials. I'm trying to be well behaved and put everything in its right folders. I have to be honest and say that when I'm developing myself, I normally do this as a post-production phase rather than as I'm going, which is a very bad habit, I know. And I'm going to create a new physics material, and I'm just going to call this bowling material. Now every object in our scene can have kind of unique physics materials applied to it. But it's often the case that sort of many of the materials can be shared, and in fact you may only have kind of 3 or 4 different materials throughout your entire game, depending on the needs. And so let's have a look. When I select the physics material in the project view, we can see that that brings up the inspector, and there's some things here I want to talk about. And here is what we talked about earlier when we said that the friction is essentially divided into kind of two properties: dynamic friction and static friction. And static friction is kind of how much effort, if you like, is or how much resistance the surface is providing to the object when it is stationary, and therefore the amount of force that it needs to get it to move. And then as soon as it's moving, the dynamic friction then comes into play. And we could see before that there was obviously too much dynamic friction, because when it hit the alley, it really did just kind of stop dead. So I'm going to turn that right down to say something like 0.1. The dynamic friction is literally a 0 to 1 range value, whereas the static friction can go to much larger values, because there's kind of like no kind of set limit really with regards to kind of how sticky or how static you want an object to be on when it's sort of mounted on a surface. And also it's quite possible that if you're like creating explosions and things in your game, they're generally done by sort of not only instantiating a particle system, but also kind of creating a huge force in the physics system, so that any objects near it kind of blow outwards away from that explosive force. And so you could have objects with like quite a high force value hitting them, and you might have some rigid bodies that you don't want affected by those, so you could give them like really high static friction values. So for me though, I'm going to put that down to 0, because it's not really playing a part here. Our ball is never going to come to rest on the alley. Okay, so the next thing, actually before we do anything then, let me assign that to our ball. Like I said, at the moment these things will have the default materials assigned, which kill quite a lot of the speed when the objects interact. They have quite a lot of friction. And I'm also going to assign the same material to the alley, because I don't want the alley or the lane to offer any resistance really, or much resistance, and I don't want the ball to have much resistance either, because in a like a 10-pin bowling arena, the surfaces are very highly polished, and the balls are very smooth, so there's very little friction happening between the two. Okay, so I've assigned that to both the alley or the lane and the ball. So let me press play and see what happens. There you go, that's looking a lot more like it, isn't it? But as you can see, I still don't like the way that the ball sticks to the alley. It's very unrealistic. After all, it is dropping down from a height here, and just look at it, it just isn't realistic at all. And that is because our material currently has absolutely no bounciness. The ball has no bounciness, and the lane has no bounciness, because they're both using the same material. So let's put up some bounciness now. This goes up, I believe, to 1 as well. Yeah, 0 to 1. So let's sort of see what it looks like at... Actually, let's have some fun. Let's put it up to 1, just so we can see what happens. Oh ho ho! Just bounced right over the top, as you can see, because it's like totally bouncy. Literally none of the force that the object is moving is being absorbed by the impact. It's like the speed at which it kind of hits the surface is like being entirely reflected, so it just goes on bouncing forever. But of course that is not how things bounce in real life. Every bounce forces it to lose some of its energy, and then the next bounce is not quite as high, and the next bounce is not quite as high, and eventually there is no more energy left with which to bounce. So I think we're going to put this down to say something like, let's try something like 0.35 and see if that looks quite realistic. I think we could still go a little bit higher, given the fact that, let's try that. I quite like that. That looked quite realistic. Let's just see this in the game view a minute. Yeah, that gave like a little bounce. Could probably even go up again, because the ball isn't really going to be thrown from that angle, is it? I mean, it's going to be lower than that. Let's try that. Yeah, and then when we move the ball down, it should be a little bit more realistic. So I've actually lost my scene view. Oh, there it is. So yeah, let's just move that ball down a little bit down so it's kind of more where the camera is, and we'll just kind of put it behind the camera as well for now so it's not blocking our view. And I can remember to fly around in the scene view, you just hold down the right mouse button and you can use the WASD keys, and it gets you where you want to go real quick. So let's try that again. We'll even go full screen on this one. Yeah, I like that. That's looking pretty good. That almost looks like a bowling game, doesn't it? So there we go. So let's go back to the physics material. So we've seen that we can tweak how surfaces interact with each other, and the bounciness surfaces, of course, very, very important for simulating different kinds of surfaces. And the last thing I want to talk about is just these two here, the friction combine and the bounce combine. And this basically just instructs Unity on what to do when two surfaces interact that have like wildly different friction or bounciness settings. For example, if the ball had a bounciness of 1, full bounciness, but the surface which it hit had a bounciness of only 0.5, what value should be used? And as you can see, the default is to take the average of those values, but you can multiply them. You can take the minimum of the two material values or the maximum of the two material values. So even if my bouncy ball hit a surface that had 0 bounce factor, it would take the maximum, which would be the one from our ball in this case, and we would have a maximum bounce. So I'm going to leave that on average. The same is true with friction. Exactly the same things apply when two objects collide that have two different physics materials. This it allows us to instruct Unity what to do. Should it take the minimum or the maximum of the two friction values? Should it take the average, or should it multiply the two together? And that's all there basically is to physics materials. And using them, you can really make the surfaces in your games and the interactions between your objects seem a lot more realistic. Okay, what we're briefly going to do now is just put some sides on this lane, because in a minute we're going to write a little script that's going to give the camera the ability to move left and right, and then you can fire the ball in that direction. And if we fire the ball in this direction and it goes off the side of the alley, it's not coming back again. It's going to fall forever. Well, either that or at least until you turn your computer off or have a power cut. But either way, not a great way to kind of restart the game if you want to throw the ball again. So the way I'm going to create some sides for our lane here is I'm just going to duplicate the lane that we've already got there, just purely because it's a cube. It's already got like a collider and everything attached to it, so duplicating that is very easy, and then I can just kind of move that to the side then like that. And what I'll also do is I'll have to make this very, very slim. I don't want it to look like a big chunky cube. And if I go to the end, I can kind of see I want it intersecting a little bit like that, and then a little bit of height on it like that. And you can see that kind of looks like a side, right? Kind of. Yeah. How does that look from the game view? Probably still a bit high, so I'll put it down, just have those 3 rivets showing. There you go, like that. And then I'm going to rename that to Right Guard, which is actually a leading brand of antiperspirant deodorant. I don't know if that's the same everywhere, but certainly over here in the UK. So I don't want it said, okay? I don't want it said by anyone that Gary Simmons is not open to a product placement deal, because I've clearly shown that is not the case. And then I'm going to duplicate that again. I should just mention that that wasn't actually, we're not sponsored by Right Guard. That was actually a joke, believe it or not. And they always say a bad joke is one that you have to explain. So there you go. Just another bad joke by Simmons. Okay, so I've got these 2 lanes here with these 2 lane guards here, and what I'm going to do is I'm going to create another one slightly behind that, just so it gives it kind of just a bit more kind of depth in the scene, if you like. And I'm probably going to apply a different texture to that actually, because we've got that metal rivets texture which we haven't used yet. And I'm going to duplicate that again, I'll call this one left guard again. I mean, I should probably call them left guard 1, left guard 2, but hey, does it really matter? It's not like there's kind of millions of objects in this scene. Although, to be fair, I've also said that when I started off with a scene that eventually ended up having quite a few objects in it, and I made the same mistake. So I want to apply a different texture to these just for the heck of it. So I'm going to go down and create a new material, and I'm going to call this material Lane Guard, and I'm going to use the metal rivets texture, this one here. We haven't used it yet, so I say, hey, we've got it there, let's use it, and we'll drag that on to our 2 rear lane guards. Actually, maybe it would look better down there. Actually, I may put that lane guard first. Yes, I think that's what I'll do. So as you can see, I've made a mistake there, but it's very easy. Just drag and drop our lane materials onto the scene. So it's a great way of I mean, look, that's what it would look like there. We don't want that, do we? And obviously what we can see when we see those 2 lane guards is because these are very thin and stretched, the object is very elongated, and therefore we're going to need to really tile this thing a significant amount in that direction, in the X direction. So probably something like 60, maybe even something like 80. Could that really be? Maybe even something like 100. Whoa. No, because they're no longer round anymore. You can often check the kind of the rivets, and then you can see if they're not still round, then you're doing something wrong. And I'm going to tile it a little bit more, see if I can get a complete thing in. Yeah, a complete kind of 4 panel thing. And I'll probably need to move that down a little bit. And what I'm doing is I'm kind of offsetting on the Y now. Although I have to say, not very successfully. There you go. So that'll do for now. We've got kind of, I'm just kind of sliding the texture up and down so that once we've got the tiling how we want it, we can control exactly, almost like kind of moving a piece of paper around on a drawing board, so to speak. So we've got that, but let's be honest, that looks horrible because it's just using the standard diffuse shader. So let's choose something a bit nicer, like a reflective bumped specular shader, which requires a environment map, which we know we already have, and a normal map, which we don't already have. So what we're going to do is we're going to take that texture, that metal rivets texture, and like we did before, we are going to duplicate it. And the hourglass is now showing up in Unity because this is a fairly sizable texture, so it takes some time. It's duplicated the texture in the project view now. It's called it Metal Rivets 1, but in keeping with my own naming convention, I'm going to put a capital normal on the end there, and that's how I call. That's how I name all my bump maps. That's just me, though. You may hate it, but of course, naming this normal does not make it so. So we have to go select it and go to the inspector and then choose the correct texture type, which is normal map, and make sure that we have ticked the create from grayscale option, which is going to create it from a grayscale version of this map, which, let's face it, it's already grayscale, isn't it? But at least it looks it. And I don't want this to be too bumpy because this is actually quite a noisy image, and it could look a bit horrible. So I've just clicked apply, and now I'm going to let Unity do its thing, and we can see that when it gets to the point where it all looks bluey and purpley, we know that it's been correctly converted to the right format. So, but it hasn't been applied to our object yet because we haven't assigned it to our lane guard material. So I've selected the lane guard material in the project view, and now I drag over the metal rivets texture, and I am reminded instantly how horrible it looks when I don't tile it correctly. So we know that this is essentially a copy of that, and that needed a 50 on the X, a 3 on the Y, and a 0.03 offset. So I want to replicate that so that the normal map kind of marries up perfectly with the base map. Oops. So that's what I'm going to do. And there we have it. So it all looks a bit white at the moment. So I think what I'm going to do is I'm going to change the main base color of the object so it looks a bit more metally. I don't want to take it right the way down. Just going to play around with the specular highlights a little bit. Not given the fact that it's kind of a cube, it's not really got a lot of stuff to play with. But so if I just let's now start to introduce in the contribution of the environment map, or the reflection cube map as they're called in Unity. And we don't want anything too over the top here. I think we could probably go with a bit more than that. But the point of this really is not really it's not really important to this application, but you just want to get used to working with the materials, the properties, and sort of dragging and dropping and new materials and stuff onto objects. So that's done. So now it's time to add some scripts to our camera and our ball. I should just mention that previously, if you remember, we had a very simple script attached to the ball, a one-liner that set its velocity and had sent it firing down the alley towards the pack of pins. But I've now deleted this, both from the ball. I removed the component, and I also removed it from the scripts folder of the project, because we no longer need it. Our new scripts are going to supersede it. So what I'm going to do now is drag in those two new scripts that I've written, and one of these, once again, we just drag and drop into the project view. One of these is called camera look, and that needs to be dragged and dropped onto the camera like so. And the other one is called release ball, and that needs to be dragged and dropped onto the ball game object. So there you go. So let's talk a little bit about what the parameters are. Now, as you can see, the one that has been attached to the ball, which is called release ball, has something called power, and power is really just the kind of the strength at which we set its velocity initially. If you remember in the old script, I think we set this initially to kind of 9, and we just hard coded it. So I've just exposed this to the inspector now. But what it's also asking us for here is a reference to a transform. Okay, because it needs to know the transform of something, and I wonder what it can be. Well, the fact that it's called this variable cam, I think it's a safe bet to assume that it wants the transform of the camera. So I'm going to drag my main camera object, my game object, and drop it over that. And remember that Unity is great in that when you drop it, a game object, over a component reference like this, it automatically understands that it wasn't the game object that I wanted to create a reference to. It was the transform component connected to that game object, and it automatically makes that connection for you. So we've got kind of a reference to the camera script and the power that we wish to fire it. Nothing too difficult there. And then when we go to the main camera of our scene and look at the camera script that we've added, this wants a reference to our ball script, not a ball object, our ball script that is called release ball. Now, once again, as I just said, the great thing about Unity is that we can just drag the game object over, in this case our ball, and it will automatically understand that it's not the game object I want to reference to, it's actually this component here, our release ball script. So now the camera has the ability to call a function in the release ball script very easily without having to search for it, and it just so happens, I think, if I go just very quickly look at the code for that, the release ball method that it calls is just called bowl. Oh yes. So in other words, what's happening here, we'll look at this in a minute, but when the camera is ready to, well, let me say that again, the camera script rotates with the mouse input. And when the user presses the mouse, the camera script detects that, and then it calls the bowl method of the release ball script. It essentially tells the ball to shoot itself down the lane. So let's test that. Oh, and also I forgot to mention there's some other parameters here. One of them is mouse sensitivity. That basically just is a way of us controlling how much kind of mouse movement maps into how much rotation. So if it's not moving fast or it's moving too fast, we can alter this value to change that. The rotation amount is essentially almost like our field of view of movement, if you like. This is basically saying that from looking straight down the alley, we are allowed to rotate from that point either 35 degrees clockwise or 35 degrees counterclockwise. Okay, so 35 degrees both ways. And finally, we've got a lag property, and this just allows the camera to look a lot sort of smoother. So when we move the mouse suddenly, the camera doesn't suddenly jerk. We can there you go, we can move it smoother so it's nice and smooth. I don't know, I think that's too smooth. So the more that you increase it, the more lag that you get. And what this is doing behind the scenes, and I'm sure as your coders, you've seen lots of in sort of lerps and slurps and things like that, and what this is doing is just kind of interpolating each time from the position we want to be at, or the rotation we want to be at in this case, from its current location based on the delta time scaled by this amount. So basically, the larger this value is, the more quickly we get where we want to go. And let's try that. Yeah, I think that's a bit better. That probably looks a bit jerky on the video capture software, but hey, it's smooth as silk here. So let's see if it works. Let's look down there and fire our ball, and there you go. It hits the side of the alley and misses the balls completely, misses the pins completely. And there you go. And if you try and press the left mouse button while the ball's going down, it actually doesn't allow you to fire another one until the ball is out of play. And it knows the ball is out of play. Do you know how? Because when it leaves the alley, did you notice I just threw it over the side then, like that? Because when the ball drops below a certain altitude, in this case I think it's when it drops below kind of -2 on the Y, we know that the ball is definitely lower than the lane at that point, and therefore the ball should be recycled and fired again. So that's basically how it works. Let's go and have a look at the code, and we'll look at the I think we'll look at the camera script first. Okay, so I'm going to open up the camera look script in MonoDevelop. Hey, there's my class. And these first 4 public members we've kind of already discussed. The first is a reference to a release ball object, and we've seen that there is a script of this type attached to our ball game object. And this camera object is going to need to be able to talk to that ball object in order to say, hey, the left mouse button has been pressed, it's time to bowl yourself down the lane. And if I actually just prematurely jump down a few lines into the update method, you'll see the line that does exactly that. This line here, it says, hey, if the mouse button has been pressed in the current frame, and you'll remember this from a previous script, that in order to get this information, we call the input classes getMouseButtonDown method, specifying a mouse button index of 0, the left mouse button. If this is true, then it means that button has been pressed, and provided we have a valid reference to a release ball object, we call that object's bowl method, and this is the method that tells the ball to fire itself down the lane towards those pins. And we've also seen that this assignment, this reference assignment, is actually made in the editor using the inspector. We did it by dragging and dropping the ball game object over the camera look script. And that automatically made that reference. So like I said, that needs to be done in the inspector. The second variable is a mouse sensitivity float, and basically what this does is this. You'll see in a moment that when we wish to rotate our camera in response to what is called x-axis movement of the mouse, in other words, horizontal movement of the mouse, when the mouse is moved left and right. And when we ask the input class to give us this information about how the mouse has moved left or right, it will actually give us that value back, in most cases in the range of -1 to +1. And this is fine. We could simply use this to increment and decrement our kind of current y-axis rotation, if you like. But we don't want to be limited to just being able to rotate 1 degree left or right per second. So we're going to want the option, at least, to magnify this up, to scale this up into a better range. So if we set this to 10, for example, then what we would be doing is when we ask the input manager to give us the mouse's x-axis movement this frame, we would be able to scale that -1 to +1 range into the -10 to +10 range, and that would allow us to have a maximum rotation of -10 to +10 degrees. So that's all that is, just kind of allows us to take the input manager's values and map them into something that makes sense to us. And then we have this rotation amount float, and as we've discussed, we need a way to limit the amount that the camera can rotate left and right from its initial kind of starting orientation, where it's just looking straight down the bowling lane. We don't want the camera to be able to move, like rotate 180 degrees and look sort of behind itself, because there's nothing back there to see. We've put no scenery back there. It all looks a bit ugly. We would just see literally just the lane, the very end of our bowling lane, and we don't want that. Would completely destroy the illusion that this is actually a AAA bowling title, wouldn't it? So yeah, we don't want to do that. Not after all the work we've put in and all those crazy good art assets. So we don't want to do that. So just by playing around inside the editor, I was able to kind of ascertain that 35 degrees left and right of that initial kind of vector that we're looking down is about right. We can't sort of spin around, but it allows us to kind of look a fair amount of degrees left and right, more than we would ever want to if we're sensibly trying to bowl the ball towards the pins. We'll see in a minute that we handle this kind of limit of rotation in a way that automatically handles kind of wrapping around the 0 to 359 degrees boundary, but more on that in a moment. But like I said, this is just saying, hey, no more than 35 degrees left or 35 degrees right from the initial, and this is the important part, from our kind of initial Y angle are we allowed to deviate. And then we have the lag, which we discussed briefly, is basically just a way for us to control the speed at which we will interpolate to our target rotations and positions. So when the mouse is moved sort of left and we want to rotate, say, 10 degrees to the left, we don't immediately just rotate the camera 10 degrees to the left, but instead we say, hey, we store that value, that 10 degrees left rotation, and then we slowly move to that over a number of frames, over a period of time. And this lag essentially allows us to kind of control the speed at which that interpolation happens. So now we want to talk about these four little babies here. In order to understand these, we have to understand how we can talk to the transform of an object, and how we can kind of both get and set its orientation. Now, the transform component in Unity allows us to both sort of fetch and set orientations in a number of different ways. Quite common is to fetch the rotation and set the rotation as a quaternion, or to fetch the rotation as like a look and an up vector. And the third method that we can fetch a description of the object's orientation is by using Euler angles. And if we ask the transform for Euler angles, it will return to us a 3D vector with an X, Y, and Z component. And each component will kind of describe the orientation of the object as rotations around those three axes, respectively. So it basically contains an X-axis rotation, a Y-axis rotation, and a Z-axis rotation. And when combined, they essentially describe the orientation of the object at that time. Now, in our scene, we actually don't need to be able to kind of pitch up and down. So we don't need to perform any kind of X-axis rotation. We don't need the camera to be able to roll left and right. So we don't need any Z-axis rotation. All we actually need is to alter the Y-axis rotation, the Euler Y angle. And therefore, what we're going to actually do is at scene startup, we're going to use this Euler's vector here. And we're going to say to the transform here, hey, give us a copy of your Euler angles at scene startup. I'm going to make a copy of them, like I said, and store them in the Euler's vector. Now at this point, we've already got a vector that we can use to kind of reset the new Euler angles each time. The X and Z are never going to change, so we can just leave those alone. They'll just be set to what they were set to when we first fetched them from the transform. So all we have to do is calculate the new Euler Y angle each frame, stuff it back in this Euler's vector, and then set this vector back in the transform. And we're going to kind of calculate new Euler Y angles and perform the clamping by doing this. When the scene first starts up, we're going to make a copy of the Euler Y angle, the rotation around the camera's Y-axis when the scene first began. And like I said, we never want the player to be able to kind of deviate more than 35 degrees left or right of this initial angle. So We're going to use this angle offset for doing that. It's going to be set to 0 initially, and when the mouse is moved left, we're going to kind of decrement some value from this. When it's moved right, we're going to add on some value to this, and we're going to make sure that it's never, it always stays contained within the -35 to +35 range. So the angle offset will always tell us how much we've deviated from the initial Y angle rotation at scene startup. So then every update, when it's time to actually set this Euler's vector back to the transform, and we need to calculate the new Y component, the new Euler Y angle, we can simply do that by adding our angle offset onto the initial Euler Y angle and then stuffing it back in this vector and then setting that vector in the transform, and all is good. And then we have this initial X. Now, in order to understand why we need that, I think I actually forgot to tell you that not only do I implement the left and right mouse movement to perform rotation left and right around the y-axis of the camera, but I've also implemented the A and D keys so that we can actually move the camera left and right across the alley, but in such a way that we still stay contained within the width of the alley. And we do that in much the same way, actually. When the scene begins, we actually make a copy of the position, and now it just so happens that that position will describe a position at the center of the alley, and all we actually want to do in this particular case is when the A and D keys are pressed, we just want to move the player along the world x-axis. So we want to either increment or decrement the x component of its position vector. The y position of its the y component of its position vector is never going to change. We don't allow the camera to go up and down in the air. And we don't, also the Z component is never going to change. We never let the camera kind of move down the alley towards the pins. So like I said, all we need to do is calculate the X component of our position each frame. And we also have this, like I said, this position vector here that's going to store the copy of those scene startups. So what's nice about doing this is we have both the Euler's vector and the position vectors, and we're just kind of altering the component each time so that we're not having to constantly recalculate a new 3D vector for these two things that causes more garbage for the garbage collection system to deal with. So like I said, at scene startup we make a copy of the position, and we also make a copy of the initial X component of its position, because we're going to kind of alter this as we move left and right. And then we're going to set the move offset to 0, and when the D key is pressed we're going to add a value onto this, and when the A key is pressed we're going to subtract a value from this. So it's always going to describe the amount that we've deviated from our initial kind of X position, our initial position along the world X axis. And if I just jump ahead into the update method, you can see that the value I clamped this to is -1.1 meters to +1.1 meters, and I simply just found those values by testing the scene, and I realized that any more than 1.1 meters deviation either left or right, we stand a good chance of falling off of our lane into oblivion, and that's not pretty. We don't want to do that. So yes, so we've got this movement offset that we just increment and decrement and keep within the -1.1 to +1.1 range, and then each update, when it's time to reset the position, all we have to do is calculate the new X component of this position, and we do that by adding our movement offset onto the initial X component that we recorded at scene startup, stuff it back in this position vector, and then set that vector back to the transform, and all is good. So let's now move on to the start method, where it's going to see it doing everything I pretty much said. First thing we're going to do is make a copy of the position of the transform, and we're also going to make another copy of the actual X component of that position, because the X component here we're going to be kind of setting and changing each frame. But we always want to know what the initial X component was so that we never deviate more than 1.1 from this. And then we set movement offset to 0. This is going to be used to obviously track how much we've moved left and right from initial X. And then we do the same for the Euler angles. We basically say, hey, give us your Euler angles, and you can see that the transform component has an Euler angles property for fetching that vector. We make a separate copy, once again, of the Euler's Y angle. Because we're always going to need to know how much we've deviated from that, how much our angle has deviated from the initial Y angle. And of course, at the scene startup, we haven't deviated at all, so we set angle offset to 0.0. Whew, that was a mouthful, I'll be honest. So now it's time to move on to the update method, and the first thing you see is me setting this boolean to true. Screen.lock cursor. What on God's green earth can that mean? And we're going to have a look at the screen class now. It's another Unity class. I'm not going to spend hardly any time on it. I just want to make you aware of it because it contains all things screen related. And it has things such as we can inquire about the current resolutions that are available, the current resolution that we're in. We can choose to show or hide the cursor. This is just a Boolean. We can inquire as to the width and height of our screen. We can, just by flipping this full screen Boolean here, we can change the game from full screen to windowed mode. And of course it even has this function here, set resolution, which allows us to change the resolution in which our game is playing on the fly by specifying a new width and height, and also specifying a Boolean as its third parameter that says, hey, we wish this to either be a full screen application or a windowed application. So this is a pretty cool class right there. But the one we're interested in right now is the lock cursor Boolean, and you're going to want to use this in most of your games because the last thing we want on the screen when we're playing a game such as a first-person shooter, for example, is the mouse cursor right in our way. That would be really annoying. So obviously we want to hide that, but there becomes a slight problem when we hide the cursor, especially if we're developing a windowed mode application, because although we've hidden the cursor, when we're kind of moving our mouse left and right, in fact, let me call up the actual game window, make it a bit easier. When we're moving our mouse left and right, although we might not be able to see that cursor, it's going to be hidden. That doesn't mean that the cursor isn't still moving left and right. Now, in the case where we're running our application in a windowed mode application, in windowed mode, it's very possible for us to move, without seeing it, our mouse outside the bounds of our window over another application window, and then when the player presses the left mouse button again, we may accidentally change focus to that other application, and this is pretty disconcerting, right? Because we're now playing a game and our game window is no longer kind of capturing any of the mouse or keyboard input, and we think everything's broken, and in fact it's not. We've just unknowingly activated another application, giving it the focus. So the lock cursor does two things. First of all, it hides the cursor. And then it locks the cursor position always to the center of our application window. So even though we can't see it, when we're moving it left and right, it's making sure that the cursor itself always stays centered. We still get the readings, we still, we know how much it's moved left and right, but just the cursor itself stays locked to the center, so we can never accidentally move it outside into another application window and accidentally shift the focus. So that's what that does. Screen lock cursor set to true basically means, hey, we don't want to accidentally click on another window. That would not be nice. So that's that. You want to use that a lot. Then in the next line you'll see that we take our lag value. Now this is a public variable, as we've seen, that is set via the inspector. And we also discussed how it controls the speed at which we interpolate to our target positions and rotations. And in this particular case, I used the clamp method to clamp it, and this is a function of Unity's MathF library. And I say that I want it clamped in the 0.01 to math infinity range. Now math infinity is the largest value that we can store in a float. So I'm saying, I don't really care, how big the value is, but I definitely want to make sure that this value isn't 0. That's the whole point of this clamp. Because later on in this function, it's actually used in the division, and if this ever gets allowed, if this is ever allowed to be set to 0, we're going to get a divide by 0 error, and everything will blow up in our faces. So we don't want that. Now I know what you're thinking. You're thinking, well, okay, but why didn't you just do that clamp in the start method, sort of here or something? Because you're clamping it every frame. Why are you doing that, Gary? Gary, tell us, why are you doing that? It seems very inefficient. Now the reason I'm doing it in this particular example is we have to remember that lag is a public variable, which means it's actually going to be declared. It's going to be accessible from other scripts, and it's also going to be it's going to show up in the inspector window when we're running it inside the editor, and therefore it's very, very possible that when we're kind of playing around with this value inside the editor when the game is running, we may accidentally set this to 0, and that would cause the divisions to, like I said, to go very, very wrong, and we don't want that to happen. So in the next line you can see that we've kind of discussed this. I just say if the left mouse button has been pressed in the current frame update, then call the ball script's bowl function that tells the ball to bowl itself down the alley. And then the next function, I use the input class again, and I use this function that we've, sorry, I said the next function, what I meant is in the next line of code, I use the input class's getAxis method, and we haven't seen this function being used before, and as you can see, I've actually passed it a string called horizontal. This is the name of the axis that I am inquiring about. Now, in order to understand what this function does, we're going to need to take a slight detour, unfortunately, and briefly discuss Unity's input manager. This is where we set up and configure all of our kind of controllers, all of the things that we wish our project to support. So let's do that now. Okay, so we open up the input manager in Unity by going to the edit menu, the project settings submenu, and selecting input, and that brings up the input manager in the inspector. And when you start create a new project in Unity, by default it will create for you these 17 virtual axes that you see here: horizontal, vertical, fire one, or these are all the names of the axes. And so what is an axis? Well, input in Unity is both a blessing and a curse. So let's talk about the blessings first of all. Let's have the good news. The good news is that virtual axes allow us to communicate with a wide variety of devices in a very device independent way. We get back consistent values in the range of -1 to +1, irrespective of the type of device that we're talking to. In fact, all of our code, for example, can use this horizontal axis to get the position of that axis, but it doesn't care about our code, doesn't care about whether that's a joystick axis, a mouse axis, or even an axis that is set up using 2 keys on a keyboard. And this is beautiful because our scripts can be blissfully unaware and use a single scripting interface to talk to any type of device. The curse, in my opinion, and I hope this is something that they change in future versions of Unity, is that the input manager is completely unconfigurable from runtime. You can't change the names or add additional axes or change the properties of those axes from your script. And this certainly has some drawbacks, and even in GeoRacing I had to work around this to some degree. But it's not so much of a problem. You just have to make sure that when you set up your axes properly, so that they're compiled and built with your application when you do your final build. So let's talk a little bit about what an axis actually is. Well, let's look at this first one here called horizontal, and if I pull down a little drop down, you can see all the properties. The first is its name, and this is the name which we inquire about the state of the axis. As we saw in our code, we're asking about an axis called horizontal. Now, our code, as you can see, doesn't care whether this is a joystick, a keyboard, or a mouse axis. All it cares about is the name, and we can set up how that axis actually works in the input manager. Now, in this particular case, it's called horizontal, and each axis has to have a type, and it can be either a key, a keyboard, or a mouse button type, kind of like an on-off type, if you like. A mouse movement type, in which case it represents the mouse moving either horizontally or vertically, or a joystick axis type, which I think needs no explanation. And if you choose things like mouse movement, you also get to choose the type of axis, either the horizontal axis, the x-axis, or the y-axis, the vertical movement of the mouse. And obviously if we choose joystick axis, we get to choose from up to 10 different axes that joystick may support. But this particular one is a key or mouse button, like an on-off type device, a digital device, not an analog one. So we have the name, and we can put things in like descriptions and things like that, but the important things are the negative and positive buttons in the case when we're using a key or mouse button device. And the obviously we're using keys to represent a virtual axis here. So we have a negative button and a positive button. Now in the case of horizontal, the left cursor key is the negative button, and the right cursor key is the positive button. And we also get a chance to specify alternative negative and positive buttons as well, which in my case I used A and D. And what's great is, irrespective of the axis that we're using, we'll generally get back results in the -1 to +1 range, irrespective of the type of device that axis is mapped to. So like I said, from our code, we can treat all of our input exactly the same, irrespective of the type of device that the end user is using. And the great thing about virtual axes is they allow us to kind of represent an analog type behavior even on a digital device. Now let me explain what I mean. In this particular example, I've said that the left cursor key goes left and the right cursor key goes right. And I also said that the values returned for an axis are in the -1 to +1 range. Therefore, we would imagine that when we press the left key, we get a -1 result back, and when we press the positive key, the right key in this case, we get +1 back. And that is indeed how it works. However, we also have the ability for Unity to filter that input and make it act a little bit more like an analog device. Now the first one is this gravity here. Now obviously when we move like a big joystick to the right, and then we let go of that joystick, it doesn't immediately snap back to 0. That joystick will take some time to return to its center point. And we don't get that in with digital devices such as keys or mouse buttons. And this allows us to kind of fake that, that whole concept. So you might imagine how I press the left key and I get back a -1 result. And then when I let go of that key, rather than snapping straight back to 0, it may slowly climb up from the -1 to 0 over a kind of a certain duration. So it's the speed at which the kind of the output value of this axis returns to its neutral state. Now we don't normally use gravity for kind of analog devices or joysticks or joypads because we just let them fall back naturally. But when you're trying to kind of mimic a joypad kind of behavior with the keys, gravity is very useful, so that as soon as you just sort of let go of the key, it doesn't just immediately snap back to 0. It slowly begins to center. And we've also got this snap property here, and the snap property is just a way of saying whether we wish it to snap from the negative to the positive button, rather than sort of climb from one to the other. So that, if you imagine that we press the left key and it was at -1, we press the right key, so it would go to +1. Do we snap immediately from -1 to +1, or do we kind of travel up through that range? And then of course we have the sensitivity. And this is only used for digital devices such as, either digital joysticks and joypads, which, I wouldn't imagine even exist anymore, and keyboards, when you're using keys on a keyboard to represent an axis. And once again, this is another way of kind of faking analog behavior. So let's say, for example, when our scene starts, no keys are being pressed on this axis, and therefore it's giving us back a result of 0 when we call get axis. But then the user presses the left cursor key. Instead of just having that immediately snap to -1, we have this sensitivity button which specifies in units per second the speed at which we're going to move from that 0 either down towards the -1 if we're pressing the left key, or up towards +1 if we're pressing the right key. So we don't just, because if you imagine you're using keys to kind of control a racing car, we certainly wouldn't want, when the user presses the right key, that to immediately give it like a full intensity turn of +1 so that the wheels just immediately spun right round. We might want to kind of press that key and let it slowly climb up from 0 to 1 the longer they hold it. And of course the same is true for kind of like mouse buttons as well. Like if you look at the Fire 1 here, this is an axis, but it's just a once again a key or a mouse button axis, and it doesn't have a negative button, it just has a positive button in this particular case. And you can see that this is set to be either left control on the keyboard or mouse button 0, in other words the left mouse button on a PC. And once again, if you were to set the sensitivity such that it slowly climbed up, then you kind of have the functionality of like almost like a power meter. Like the longer they hold the mouse button down, the kind of the larger and larger the reading would be as it slowly moved up from 0 to 1. And then of course, what else have we got here? We've also got the dead zone, and this is basically only used when we have an analog device, such as an analog joystick or joypad controller, and that just allows us to define like an area where any slight movement, any slight deviation of the angle of the stick off center point doesn't actually register and still returns a value of 0. So and finally, obviously, we have the invert property here, which, as you would imagine, just flips the positive and the negative of the reading. So if we were to set invert here, then pressing the left key would actually generate eventually a value of +1, and the right key a value of -1. So we've seen that we can set up these virtual axes for either keys, mouse, or joystick or joypad controllers. And this is really cool. You know, it allows our code to deal with it in a very device independent way. But what's also really good is that if you look down here, we can see that there is another axis that is defined with exactly the same name, horizontal. And this particular axis isn't a key or mouse button axis, is actually a joystick axis. And in this particular case, I'm saying I want this horizontal axis, this virtual axis, to be mapped to any joystick x-axis, so the x-axis of any joystick that may be plugged in. And I don't bother obviously setting the negative and positive buttons because this isn't a key or a button type. This is an axis type, a joystick axis type. So what does that basically mean? We have two completely different virtual axes, both with the same name. And this is what's really great about the input manager, is that Unity will automatically kind of look at both of those things and use the one that's most influential. So we can just create a keyboard axis called horizontal and a joystick axis called horizontal, and then in our code we don't really care which one's being used. The user could be using a joystick or could be using the keys. All we're saying is get axis horizontal, and like I said, the input Unity will automatically, if the keyboard's being used, it will use these settings to return the value, and if the joystick is being used, it will return these values. And in any case where both of them are being used, very unusual, but just in case there is, Unity will send back the result of the one that is kind of the most influential, the one that has the most extreme kind of reading. So very cool way of defining different controllers and mapping them, different controller types, all to the same axis name. And in our code we can just say get axis horizontal, and you know, we don't care if it was generated by the joypad, the mouse, the joystick, or keys. We just get our -1 to +1 range back. So that's what input get axis is doing here. Now, like I said, I think I've said this. If I haven't, I'll say it again. The bad news about the input manager is that it's almost completely unconfigurable from script, which means we are completely unable to add more axes, delete axes, change the settings of axes via our code. And this obviously causes some problems. It caused me some problems in GI Racing, which I had to work around. And it's nothing that you can't work around, but you do have to make sure that you set up your axes correctly, you know, prior to publishing the build of your application, okay? Because all of these settings, the input manager will be published with your application when you publish the build. So we now know that when we call input get axis and then specify an axis of horizontal, what we're actually saying to the input manager is give us back a -1 to +1 reading that is generated either from the user pressing the A or the D key, the left cursor or the right cursor key, or by moving a joystick or joypad controller stick left and right. And like I said, this comes back in the -1 to +1 range, and that's a little too much. We're using this to move our camera left and right, and as we've already discussed, we actually only allow a maximum movement of -1.1 to +1.1 from, you know, from left to right. So we certainly don't want to be moving 1 unit per frame. So as you can see, I multiply this by 0.1. I essentially say, hey, we're going to only take sort of 10% of the strength of that axis and use that. So we're just using a smaller value than is returned by the get axis, and I store this in this delta x float. And then all I do now, I've got this sort of value in the in the -0.1 to +0.1 range, is I subtract that from our movement offset, which remember starts at 0. Now the reason I subtract it is because I've taken a bit of a shortcut in this application. I'm not kind of I'm just moving the camera down along the world x-axis. I'm not moving the camera sort of along its own right vector, if you like. And therefore, because our camera is rotated 180 degrees, I believe. I choose our camera. Yes, there you go, 180 degrees. That means that pressing left actually causes us to move right, and pressing right causes us to move left. So what I've decided to do is just flip the sign here. But like I said, probably a way that you would do this in production code is you'd actually ask to transform for the right vector and then kind of move ourselves along the camera's right vector by that amount. So what we're doing here is using the mouse input to just kind of alter our movement offset either left or right. And then of course, like I said, we use once again the clamp method, which is part of Unity's MathF class, to clamp our movement offset in the -1.1 to +1.1 range, so it never kind of goes outside the bounds of the bowling lane. And then at this point, we know what the actual world kind of space position of our camera should be. We know that the X and the we know that the Y and the Z position haven't changed, and we've got those stored in our position vector up here. So we just need to calculate the new X position, and that really, like we said earlier, is just calculated by adding our movement offset onto the initial X value of our position component at scene startup. But rather than just set that as the new X position of our transform, what we actually do is we use the lerp function, which once again is part of Unity's MathF library, and we say that we want to kind of lerp from our current X position to this new X position that we've just calculated, but we want to go there, we want to linearly interpolate to that new position over some time. Now, if you imagine that this isn't here and we just are scaling this by time delta time, then what we're basically saying is we want to move there over the space of a second. Okay, but what I've done is I've actually created this lag value, and we do 1 over lag value. And the only reason I do 1 over lag is because obviously if I didn't do that, then a higher lag value would actually create a speedier linear interpolation to the new value, and that seemed wrong to me. To me, if you specify the lag as being larger, you expect it to be slower, so I just do 1 over lag to correct that. So that just allows us to change the speed from, like I said, from the kind of the 1 second mark, if you like. I mean, it's not really 1 second. I mean, all we're really saying is that we know that time delta time is a small amount of time that is kind of fluctuates with frame rate, so that it allows our game to be frame independent. And then we're just boosting that or reducing it by some amount to get the actual speed that we move from this position to that position. Okay, and then once we've done that, we've got the new X component of our position vector. Like I said, Y and Z are already stored in there from when we did the initial sort of get transform at the beginning. So then all that's left to do to update the position of our game object is just simply assign that position vector to the transform's position, and everything's done. And then once again we do another kind of get axis call, but this time we specify the mouse X axis. And if we go back to our input manager by once again going edit, project settings, input, you can see that mouse X is set up as a mouse movement type axis, and we're telling it that it's actually the X axis that this is mapped to, and that is seen by Unity as being the horizontal movement of the mouse. And once again, although this would generally give a result in the -1 to +1 range, it is possible in the case of a mouse movement, given of course how fast a mouse can move from left to right, that it may actually be outside of this range. It may be kind of 2 or 3, -3 to +3, but generally speaking, providing that the mouse movements aren't so kind of erratic, they'll be in the -1 to +1 range. And we get this value and we multiply it by our mouse sensitivity so that we can give it a boost, so that we're not just limited to rotating -1 or +1 degree per second. And we store that in delta Y, and now we have the amount that we wish to kind of either increment or decrement our angle offset, and that's what we do next. We add it onto our angle offset, and then of course we use the clamp method once again of Unity's MathF library to just make sure that that angle offset is never kind of goes outside the -35 to +35 range. And you can see that we clamp it to that minus rotate amount plus rotate amount, because we never want to deviate more than, in our case, 35 degrees either left or right of the initial Euler Y angle. And at this point we have everything we need to kind of create our new Y rotation, and that's simply calculated by adding our angle offset onto the initial Euler Y angle that we recorded at scene startup here. But we don't just want to set that as the new Y rotation in our Euler's vector. Instead we use the MathF lerp function to smoothly move from our current Y rotation to this new Y rotation over some period of time that we can control by lag, and that is kind of independent of frame rate, if you like. And then that's our new Euler Y angle for the current frame. So all that's left, we've got our Euler's vector now. We don't need to recalculate the X and Z components because they haven't changed since they were first recorded at scene startup. So the next thing to do is simply set that Euler's vector back into the transform by assigning our Euler's vector to the transform.Euler angles property. And there you go. There's our camera look script all done and dusted. So that's the camera look script taken care of. The next thing we need to look at is the release ball script, because we've seen in the update method of this script that if we have a valid release ball object reference, then we call its bowl method when the mouse button is pressed. So let's go and have a look at that script now. We can see that at the top it has two public variables. We've seen these in the inspector already when we first made our assignments, and we know that the first one is a reference to a transform, which we use to kind of create a link between this object, this script should I say, this component, and the transform of the camera that is in the scene, and we're going to need that in the bowl method so that we can line up the ball with the camera's kind of current orientation. And we also have this power setting which controls the speed or force at which the ball is thrown down the alley. And you could imagine that if you decided to take this further and really get serious about making your own bowling game from it, that power setting, which is currently only sort of tweakable in the editor, in the inspector, you could make like a graphical display meter for that, so that when the user presses the button, this power meter starts to build up, and then when you hit it, it takes the current reading and uses that power to send the ball down the alley, much like kind of many golf games. And the other thing that I had to do, which is what this private boolean is all about, is I didn't want the user to be able to kind of launch the ball down the alley while the ball is already moving down the alley. It has to be kind of it has to be out of play in order to be reused again. So I created a boolean called in play, and the basic concept is that the ball is, once the ball has been released by it being bowled, by the fire button being pressed, this is set to true, and it stays in play until the altitude is found to drop below -2 on the world Y axis, because this means that at that point the ball has dropped below the alley. So it's just going to continue to fall into oblivion, so there's no harm in the player pressing the fire button again at that point and launching another ball, which we can of course reuse that ball that is currently falling into oblivion. So let's have a look at how it works. First thing I didn't do it in the last script, and I should do, and I didn't, and I'm disgusted at myself. I am utterly disgusted, but I didn't cache the transform components like I said you want to do, because if you remember, every time you call one of these properties, it can be doing a get component call behind the scenes. So what I do is I define my own rigid body called my rigid body, and then in the start method I use the rigid body property to get that component and cache it in my own variable. And if we go to the update method, you can see that it basically does the following. Once the ball is in play, it literally says if the ball is in play and the rigid body's position is smaller than -2, then set in play to false. And when in play is set to false, that means when the camera calls the bowl method, this code will be executed. If the ball is already in play, then it won't be executed, but the minute it falls off the end and goes out of play, this code gets executed when the camera calls it in response to a mouse button press. And we can see that what the rigid body does, or what the code does, sorry, is it sets the position of the rigid body, essentially the position of this object's transform, the ball, to that of the camera. So we're moving the ball to the camera's position, and then we are setting, in just a one-off set, we are setting the velocity of the rigid body equal to the camera's forward vector, so that gives us our direction, because bear in mind that's a unit length vector, and then we scale that that unit length direction vector by the power at which we wish to throw it. or the velocity at which we wish to throw it. And then we set the in play to true, because at this point we've already set the ball rolling down the alley, and we don't want the player to be able to continually press the mouse and keep bowling balls down the alley. So that's pretty much everything taken care of there. Pretty simple script, that one. Now, when we go back, I would like to, just before moving on with this, I would like to discuss a slight problem with our little example, or it might be depending on what you feel about it, but I don't like the fact that I can throw a ball over the side of my alley. That's not cool. I'm telling you, that is not cool at all. So what we're going to do is we're going to show, and this allows me to show you the concept of colliders as standalone things, not necessarily always attached to renderers. And this concept of glass walls is used in games quite a lot. So let's say, for example, I don't wish to physically add any geometry there. I still want to keep it black, but I don't want the ball to go over the side. What I can do is I can select the lane, like I've done, and I can duplicate the lane. Then I can move this out. Oop, I'll move it up a little bit, like so, and then I'll duplicate that. And then, of course, I will flip the sign on the Y, and what we've got here is, without a doubt, the ugliest skittle alley I have ever seen, or the ugliest 10-pin bowling alley I have ever seen. But you will remember that when we started talking about rigid bodies at the beginning of this section, we said that the meshes themselves are not used at all. It is the colliders are the only things that are used by the physics simulation, in which case that must mean that we don't really need the meshes at all. We just need the bounding boxes, and they've already been generated. So we can now go over to the inspector for these two objects, and notice, however, that because I've now selected these two objects, that any action I do in the inspector will apply to both of them. So what I'm going to do is I'm going to actually remove the mesh renderers. We don't need them, and I'm going to remove the actual cube mesh filter. Don't need those either. All we've got left now is a transform and the actual collider itself. And this is a really good example of how we can use invisible walls. And you often see this a lot to stop characters wandering out of a game zone, or just for things like this where throwing it over the wall would not be cool. So let's just test that. As you can see, no way to get it over the side now, and that's made our simulation much more kind of stable. Now, of course, in real life you probably wouldn't want in a game like this it hitting an invisible wall, but it is still worth me showing you anyway, because this technique of invisible kind of colliders and invisible triggers is very useful. I want to just talk about the different collider types before moving forward. We've already seen how easy it is to add one of the primitive collider types. We simply we select our object, so for example our leading pin, and then we go to the component and menu, the physics submenu, and we choose any of these primitive colliders. In our case, we chose a box, and we saw that when we added this, Unity automatically sized the collider so that it tightly bounded our object as closely as possible for the shape that we'd chosen. And of course it does this by taking the data that's stored in the mesh filter and then sort of generating a bounding volume from it. Now, for our dynamic objects, our objects that have non-kinematic rigid bodies attached, we really want to try and use just the primitive colliders to represent them if we can. Now, there is another collider type called the mesh collider that will much more accurately model the shape of the object, but using it has some caveats. Firstly, if we add the mesh collider to one of our pins, for example, we would no longer be able to use the continuous or continuous dynamic collision methods. Only discrete is supported when the dynamic object has a mesh collider attached. And also the mesh collider is much more computationally expensive for the physics system to work with, and it's not able to model responses quite so accurately. Like I said, this is all in the case where you're adding a mesh collider to your dynamic objects. But mesh colliders are ideal for representing your environment, your static scene geometry. If we imagine, for example, we had the model of a racetrack or of a science fiction space station, it would be an arduous task to try and generate collision data for this by placing a series of primitive colliders. Our environments are just way too complex for that in modern computer games. And we'll see in a minute that I'll load in some other projects that I've been working on, and I'll show you basically how I used mesh colliders to generate all the collision data for the entire static scene with literally just the touch of a button, or in this case, the selection of a menu item. But I will just say here that before we move on, I will just say that it is possible to use mesh colliders for your dynamic objects. And there are times when you just have an object that is such a shape that it's very hard to even build a compound collider that's built from primitive colliders to accurately represent it. And in this case, mesh colliders often have to be used. But in order to make them more efficient and more accurate, if you like, for the physics system to model, what often happens is the artist will generate a sort of two versions of the mesh. If I use a racing game, for example, the actual car model that's used in the game, the one that's rendered, the one that's contained in the mesh filter, may be a very high polygon object, you know, that models all the headlights, the windows, the wheels, the wheel trims, and that wouldn't make an ideal candidate for a mesh collider because it's just too high in its polygon count. But what the artist will often do is then create a very, very, very low resolution version of that mesh with all of these sort of the fine detail stripped away. So what you've essentially created is a kind of a custom bounding volume shape. And in those cases, you can use this to generate the collider data. And this is often used in a situation where the primitive collider types will not suffice by themselves. So let me just show you what it looks like if we add a mesh collider to our pin, for example. So I'm going to go to the inspector for it, and I'm going to temporarily remove our box collider, and then I'm going to go to the components menu, the physics submenu, and I'm going to choose mesh collider, and the mesh collider has been added. Now I know what you're thinking, I cannot see it, nothing has happened. And the reason why you can't see it is because the polygon data that is being rendered to show us what our mesh looks like is now exactly the same as kind of the polygon data of our collider. So it's essentially they're both being drawn over one another. If I actually disable the mesh renderer, we'll see just the collider left. And as you can see, the collider is now an exact representation of our pin. But once again, I have to reiterate, you really wouldn't want to use this for our pins in this example. You want to use the primitive types, especially on your dynamic objects, your objects with non-kinematic rigid bodies attached. So let me just remove the mesh collider. Oh, actually, before I go on, let me just talk a little bit about how you could create a compound collider if you weren't happy with just using the box. And the way that compound colliders work is you create multiple child objects of the parent object that has the rigid body attached. And then each one of those child objects can have a collider attached to it. And the physics system, because these are both underneath the rigid body in the hierarchy, they're both children of the rigid body, it will see these kind of both of these shapes as a combined volume when it works with it. And we would just simply do that if you imagine we selected our pin here in the hierarchy view, and then we created two empty game objects. I'm not actually going to do it, but if I created two empty game objects, and then on one game object I could create a box collider, and I could resize that box collider so it kind of roughly bounds the bottom section, the bottom half of our pin, and on the other child object I could add a sphere collider and maybe resize that so that it kind of roughly bounds the top of the pin. And once again, because these are both child objects of the main pin object that has the rigid body attached, the system would see this as being kind of one connected sort of single volume, a single hull. In other words, those two colliders won't go kind of bouncing off in their own directions because they haven't individually got rigid bodies attached to them. If we did want them to behave as two distinct bodies, in that particular case we would add a rigid body to each of the colliders. So I'm going to remove that mesh collider now, and I'm going to re-add our box collider like so, and re-enable the mesh renderer so we can see what we're doing. And we've got it back to how it was before. So what I'm going to do now is I'm going to load in a few scenes, and we'll see how mesh collider data might look on a more sophisticated level. So here we are in a scene from GI Racing, and this is the Fiorano racetrack. And as you can see, I've got the object selected, kind of the whole scene selected, so we can see all the wireframe outlines of all the polygons that comprise it. And there's some pretty complex shapes in here, and we certainly wouldn't want to try and hand place a load of primitive colliders to try and accurately represent the shape of that track. Unfortunately, we don't have to. And I'll show you how, when I imported this scene, how quickly I was able to generate the mesh data for the static geometry. In this case, if you look in the hierarchy view, you can see that all of the static game objects that comprise the scene are all under this Fiorano parent object, which is just a kind of an empty game object that does nothing more than act as a container. But as I step through the various objects and select them in the hierarchy view or in the scene view, we can see that the mesh is made up of several submeshes, should I say. The scene is made up of several submeshes. Each can be individually selected, and each exist under that parent Fiorano game object. So what I did when I loaded this scene in is I would just simply select every object in the static scene, and then I would go to the Components menu, the Physics submenu, and I would choose Mesh Collider. And when I click that, Unity will automatically iterate through every one of those objects, fetch the mesh data, and then add a mesh collider to each one with the data already contained in it to accurately represent the polygon data of the mesh. And we can see this if I go to, let me see what would be a good example. If I select the main track, for example, like so. This is the main racetrack that the cars need, obviously, to collide with. We don't want them falling through the road. And I just remove the mesh renderer. You can see that there is the mesh collider for our racetrack. Once again, if we go and select something else, like these buildings here, there you go. I've turned off the mesh renderer, and you can see that it's created the mesh collider perfectly. This middle section, obviously, there's quite a lot of data here. Once again, turn off the mesh renderer, and there is the collider, the mesh collider information that was generated for it. And this is great. Like I said, this is where mesh colliders come in really, really useful. So I was able to literally add all of the mesh colliders to my scene with literally just a selection in the hierarchy view of all those objects, and then a menu selection here, Component Physics, Mesh Collider. Now, obviously, when you do that, there are several objects in your scene or sections of your scene that you just don't need to have mesh colliders, and you would get rid of these. Like, for example, this village over here. It's kind of like a village or hamlet or a little collection of buildings, shall we say. Now, obviously, because I selected the whole scene, it's generated mesh colliders for these, but that would be completely useless because the cars can never get over here. So we can always go afterwards and remove the mesh colliders just by doing remove component from anything that we don't need. Like this is the same here, this building here. We'd never need that because they can never get past these walls here to get to that object. So we don't need to model collisions with it. And the same obviously with these buildings here. The car can never get into this section, so we don't need mesh data for it. But hopefully you can see how simple it is to simply select the objects and then add a mesh collider. And then of course you would also then, after you've generated those mesh colliders, you would then add your physics materials to those colliders. And once again, this could be done by selecting multiple objects and then just dragging and dropping the physics material over in the inspector. And because you've got multiple objects selected, this allows you to add the material to multiple objects colliders at the same time. I think in GI Racing we had like 2 or 3 materials in total. There was like the main kind of wall colliders, which described how how the cars interacted with the walls, the track barriers, if you like. And then there was like a track surface collider, which actually I don't think I used in the end because I ended up using wheel colliders, which we'll talk about in the GI Racing workshop. So that was how I generated the static mesh geometry. The cars themselves were dynamic objects, and they were created using primitive colliders. And as you can see, I've actually used 2 box colliders to represent my car. Now I could have used a kind of a really low polygon version of like the mesh data that could have made a more tightly fitted bounding volume, but I first started off with the 2 bounding volumes, the 2 bounding cubes, sorry, and it kind of worked really well, so I thought there was no point changing it. And obviously, as we've stated, because these are rigid bodies and they're dynamic objects, and I actually want, in some cases, especially with the player's car, to use continuous collision detection to get more accurate responses and detection of collisions, I really didn't want to use a mesh collider on these objects. So, as you can see, that's a classic example of using the mesh collider to represent the scene and the primitive collider types to represent the actual dynamic objects, the rigid bodies in your scene. Now at this point, I had my cars sort of driving around the track and seemingly at least flawlessly working with my collision data, and I was feeling pretty proud of myself. I immediately went out and I bought myself a 15-inch triple pepperoni pizza with peppers and onions. I really felt that I was king of the world. But actually my problems were not solved, and the reason being is that if we take a look at, say, this section of wall here, when I generated the mesh collider data for this, obviously it's not very high, and the same over here. These walls, these track barriers, aren't really very high, so obviously the mesh colliders generated for them weren't very high. And there were situations where if the car kind of runs into this wall at, like, I don't know, say 180 miles an hour, it could actually bounce over the top and end up in an area of track that it could or an area of the scene that it could no longer get back onto the track. Especially here, look, there was actually no way to get back into the race. And this presented a real problem, because what I needed was these walls to essentially have colliders that were much, much higher than the actual mesh data would suggest. And therein lies the clue to the answer. What I decided to do was select my track barriers and remove the mesh colliders that were generated for them by Unity. And then what I decided I needed was a separate copy of just the track walls of the scenes that had their faces extruded really high up into the air. And because I'm not very good with 3ds Max, or at least it takes me forever to get things done, I pulled my old buddy Adam Holt and into this from he was busy doing his carbon development, but I pulled him in and said, buddy, I need your help. I need some really high walls. I've tried doing one track. I think I did the Bathurst track, and although it worked out all right, it took me about 8 hours just to kind of extrude all the geometry. And Adam was able to kind of do this very, very quickly because he knows what he's doing and I don't. So all of this stuff we wanted to have extruded. So he was able to, oops, sorry, I hit the mic there. He was able to load the scene back in to 3ds Max and remove everything except the walls, and then he was able to extrude all of those up, and he also was able to make them thicker this way so that the walls weren't too thin, and therefore there was a reduced chance of like a collision being missed, where like one of the AI cars might be hit a wall so quickly that it becomes embedded or passes through it. I mean, that's always a problem that's going to exist a little bit, but you try to minimize it as much as you can. And then when Adam had made this sort of secondary version of the scene that had everything removed except the extruded track barriers, I was able to load this in, and as you can see right there is the resulting colliders that I generated from the scene that Adam gave me. Now once again, if I just disable the main sort of mesh data, that's the little car as you can see there, and once again select, this is essentially the shape of the mesh data that Adam was able to give me. with all the track barriers extruded very, very high. And then what I would do is I would just add a mesh, select this, add a mesh collider to it. And then once the mesh collider had been generated, obviously I didn't want these big ugly walls in my scene, so then I was able to just simply remove the mesh filter and the mesh renderer. We didn't need them anymore, and then that just left me with the shape of the big walls, but without actually having the big thick walls in our scene. And then that, because it's exactly the same scale as the original track, I can just position it in exactly the same place, and then they both work flawlessly together. So we think that we've got these little walls, but what we've actually got is these massive walls that look like so. So there's a really good tip. This is kind of what I was talking about in the last section when I was showing you the invisible walls concept. And here you can see we've used that here. We've made these invisible walls really, really high. So yes, so I think that probably covers everything to do with adding of mesh colliders and primitive colliders. So what I'm going to do now is I am going to load in another level, and I'm going to talk about how colliders can be used as triggers.